An orbital propellant depot is a cache of propellant that is placed in orbit around Earth or another body to allow spacecraft or the transfer stage of the spacecraft to be fueled in space. It is one of the types of space resource depot that have been proposed for enabling infrastructure-based exploration. Many different depot concepts exist depending on the type of fuel to be supplied or its location. In space, fuel depots are not necessarily located near or at a space station. Potential users of in-orbit refueling and storage facilities include space agencies, defense ministries and communications satellite or other commercial companies. Satellite servicing depots would extend the lifetime of satellites that have nearly consumed all of their orbital maneuvering fuel and are likely placed in a geosynchronous orbit. The spacecraft would conduct a space rendezvous with the depot, or vice versa, and then transfer propellant to be used for subsequent orbital maneuvers. Intelsat has recently contracted for an initial demonstration mission to refuel several satellites in geosynchronous orbit, beginning in 2015. A low Earth orbit depot primary function would be to provide propellant to a transfer stage headed to the Moon, Mars, or possibly a geosynchronous orbit. Since all or a fraction of the transfer stage propellant can be offloaded, the separately launched spacecraft with payload and/or crew could have a larger mass or use a smaller launch vehicle. With the LEO depot, the size of the launch vehicle can be reduced and the flight rate increased, which may reduce the total launch costs since the fixed costs are spread over more flights and fixed costs are usually lower with smaller launch vehicles. A depot could also be placed at Earth-Moon Lagrange Point 1 or behind the Moon at EML2 to reduce costs to travel to the Moon or Mars. Placing a depot in Mars orbit has also been suggested. LEO depot fuels. For rockets and space vehicles, propellants usually take up 2/3 or more of their total mass. Large upper-stage rocket engines generally use cryogenic fuels like liquid hydrogen and liquid oxygen because of the large specific impulse possible, but must carefully consider a problem called boil-off. The boil-off from only a few days of delay may not allow sufficient fuel for higher orbit injection, potentially resulting in a mission abort. Lunar or Mars missions will require weeks to months to accumulate tens of thousands to hundreds of thousands of kilograms of propellant, so additional equipment may be required on the transfer stage or the depot to mitigate boil-off. Non-cryogenic, Earth-storable liquid rocket propellants including RP-1, hydrazine and nitrogen tetroxide, and mildly cryogenic, space-storable propellants like liquid methane and liquid oxygen, can be kept in liquid form with less boil-off than the cryogenic fuels, but also have lower specific impulse. Additionally, gaseous or supercritical propellants such as those used by ion thrusters include xenon, argon, and bismuth. Propellant launch costs. Ex-NASA Administrator Mike Griffin commented at the 52nd AAS annual meeting in Houston, November 2005, that, at a conservatively low government price of $10,000 per kilogram in LEO, 250 amount of fuel for 2 missions per year is worth $2.5 billion. At government rates, if one assumes that a 130 metric ton launch vehicle could be flown twice a year for $2.5 billion, the price is about $10,000 per kilogram. Cryogenic depot architectures and types. In the depot-centric architecture, the depot is filled by tankers, and then the propellant is transferred to an upper stage prior to orbit insertion, similar to a gas station filled by tankers for automobiles. By using a depot, the launch vehicle size can be reduced and the flight rate increased. Since the accumulation of propellant may take many weeks to months, careful consideration must be given to boil-off mitigation. In simple terms, a passive cryogenic depot is a transfer stage with stretched propellant tanks, additional insulation, and a sun shield. In one concept, hydrogen boil-off is also redirected to reduce or eliminate liquid oxygen boil-off and then used for attitude control, power, or reboost. Other active cryogenic depot concepts include electrically powered attitude control equipment to conserve fuel for the end payload. Heavy lift versus depot-centric architectures. In the heavy lift architecture, propellant, which can be 2/3 S or more of the total mission mass, is accumulated in fewer launches and possibly shorter time frame than the depot-centric architecture. Typically, the transfer stage is filled directly and no depot is included in the architecture. For cryogenic vehicles and cryogenic depots, additional boil-off mitigation equipment is typically included on the transfer stage, reducing payload fraction and requiring more propellant for the same payload unless the mitigation hardware is expended. Heavy lift advocates state that the total mass to orbit required for a mission can actually increase because of the need to launch more propellant, tanks and boil-off mitigation hardware. Heavy launch vehicles are not developed, so these costs are added to the trade, rather than using existing smaller rockets. Heavy lift advocates question the cost model for propellant depots and cite the need for development and demonstration. Depot advocates claim this increase in mission mass would be offset by a decrease in the cost per launch and the elimination of the fixed cost sieve, the heavy lift launch vehicle when not required in a given time frame. Further, long-life components including insulation, power and cryocoolers could be placed on the depot and not expended, further reducing the mass per mission and hence costs. Heavy lift is compared with using commercial launch and propellant depots in this PowerPoint by Dr. Alan Wilhite given at FISO Telecon. Feasibility of propellant depots. Studies have shown that a depot-centric architecture with smaller launch vehicles could be $57 billion cheaper than a heavy lift architecture, over a 20-year time frame. The cost of large launch vehicles is so high that a depot able to hold the propellant lifted by 2 or more medium-sized launch vehicles may be profitable. In a 2010 NASA study, an additional flight of a conceptual Ares V heavy launch vehicle was required to stage a Mars mission due to 70 tons of boil-off, assuming 0.1% boil-off day. The study clearly identified the need to decrease the boil-off rate by an order or magnitude or more. Approaches to the design of low Earth orbit propellant depots are discussed in the 2009 Augustin report to NASA, which examined the then-current concepts for in-space refueling. The report determined there are essentially 2 approaches to refueling a spacecraft in LEO. A single tanker performs a rendezvous and docking with a spacecraft on orbit, transfers fuel and separates. Much like an airborne tanker refuels an aircraft, many tankers rendezvous and transfer fuel to an in-space depot. Then at a later time, a spacecraft docks with the depot, fuels, and departs Earth orbit. The Augustin report found both of these concepts feasible with current technology, but in need of significant further engineering development and in-space demonstration. The report concluded that, with some development investment, long-term life cycle savings may be obtained. Advantages. Because a large portion of a rocket is propellant at time of launch, proponents point out several advantages of using a propellant depot architecture. Spacecraft could be launched unfueled and thus require less structural mass. An on-orbit market for refueling may be created where competition to deliver propellant for the cheapest price takes place, and it may also enable an economy of scale by permitting existing rockets to fly more often to refuel the depot. If used in conjunction with a mining facility on the Moon, water or propellant could be exported back to the depot, further reducing the cost of propellant. An exploration program based on a depot architecture could be cheaper and more capable. NASA studies have shown cheaper and faster alternatives than the heavy lift launch system and list the following advantages. tens of billions of dollars of cost savings to fit the budget profile, allows first lunar mission by 2024 using conservative budgets, launch every few months rather than once every 12 to 18 months, allows multiple competitors for propellant delivery, reduced critical path mission complexity, history and plans. Propellant depots were proposed as part of the space transportation system in the mid-1960s. In October 2009, the Air Force and United Launch Alliance performed an experimental on-orbit demonstration on a modified Centaur upper stage on the DMS-P-18 launch to improve understanding of propellant settling and slosh pressure control. RL-10 chill-down and RL-10 two-phase shutdown operations. The light weight of DMS-P-18 allowed 12,000 pounds of remaining LO2 and LH2 propellant, 28% of Centaur's capacity, for the on-orbit demonstrations. The post-spacecraft mission extension ran 2.4 hours before executing the deorbit burn. NASA's Launch Services Program is working on an ongoing slosh fluid dynamics experiments with partners called CRYOTE. ULA is also currently planning additional in-space laboratory experiments to further develop cryogenic fluid management technologies using the Centaur upper stage after primary payload separation. Named CRYOTE, or Cryogenic Orbital Testbed, it will be a testbed for demonstrating a number of technologies needed for cryogenic propellant depots, with several small-scale demonstrations planned for 2012 to 2014. As of August 2011, update, ULA says this mission could launch as soon as 2012 if funded. The ULA CRYOTE small-scale demonstrations are intended to lead to a ULA large-scale Cryosat flagship technology demonstration in 2015. The Future in Space Operations Working Group, a consortium of participants from NASA, industry and academia, discussed propellant depot concepts and plans on several occasions in 2010, with presentations of optimal depot locations for human space exploration beyond low Earth orbit, a proposed simpler first-generation propellant depot and 6 important propellant depot-related technologies for reusable cislunar transportation. NASA also has plans to mature techniques for enabling and enhancing space flights that use propellant depots in the cryogenic propellant storage and transfer mission. The Cryostat vehicle is expected to be launched to LEO in 2015. The Cryostat architecture comprises technologies in the following categories: storage of cryogenic propellants, cryogenic fluid transfer, instrumentation, automated rendezvous and docking, cryogenic base propulsion. The Simple Depot mission was proposed by NASA in 2011 as a potential first PTSD mission, with launch no earlier than 2015, on an Atlas V551. Simple Depot would utilize the used Centaur upper stage LH2 tank for long-term storage of LO2, while LH2 will be stored in the Simple Depot LH2 module, which is launched with only ambient temperature gaseous helium in it. The SDLH2 tank was to be 3 meters diameter and 16 meters long, 110 cubic meters in volume, and store 5 amount of LH2. At a useful mixture ratio of 6:1, this quantity of LH2 can be paired with 25.7 amount of LO2, allowing for 0.7 amount of LH2 to be used for vapor cooling, for a total useful propellant mass of 30 mount. The described depot will have a boil-off rate of approaching 0.1% per day, consisting entirely of hydrogen. In September 2010, ULA released a depot-based space transportation architecture concept to propose propellant depots that could be used as way stations for other spacecraft to stop and refuel, either in low Earth orbit for beyond LEO missions, or at Lagrangian point L2 for interplanetary missions. At the AIAA Space 2010 conference, The concept proposes that waste gaseous hydrogen, an inevitable byproduct of long-term liquid hydrogen storage in the radiative heat environment of space, would be usable as a monopropellant in a solar thermal propulsion system. The waste hydrogen would be productively utilized for both orbital station keeping and attitude control, as well as providing limited propellant and thrust to use for orbital maneuvers to better rendezvous with other spacecraft that would be inbound to receive fuel from the depot. As part of the depot-based space transportation architecture, ULA has proposed the Advanced Common Evolved Stage Upper Stage rocket. ACE's hardware is designed from the start to as an in-space propellant depot that could be used as way stations for other rockets to stop and refuel on the way to beyond LEO or interplanetary missions, and to provide the high-energy technical capacity for the cleanup of space debris. In August 2011, NASA made a significant contractual commitment to the development of propellant depot technology by funding 4 aerospace companies to define demonstration missions that would validate the concept of storing cryogenic propellants in space to reduce the need for large launch vehicles for deep space exploration. These study contracts for storing, transferring cryogenic propellants and cryogenic depots were signed with Analytical Mechanics Associates, Boeing, Lockheed Martin and Ball Aerospace. Each company will receive $600,000 under the contract.